This is the final module on the course on linear algebra. My name is Jay Krishnan and I'm an instructor for one of the batches. The final module deals with inner product spaces. So far, our study of linear algebra has been very algebraic. We mainly concentrated on algebraic features like linear transformation, matrix representations, eigenvectors, eigenvalues, and so on. We now introduce geometry into the picture by using an inner product. The inner product is nothing but an extension of the standard dot product that you have studied for R2 and R3 in your high school. Inner products allow us to study geometric notions like length and angle. That's their primary use. For simplicity, our treatment will restrict ourselves to vector spaces that are Rn and Cn. Whatever I say have appropriate extensions to an arbitrary vector space over R or C, but I will not dwell too much on the arbitrary case, focusing only on the concrete case of Rn or Cn. Let's first define the standard inner product. Given two vectors x equal to x1 to xn in Rn and y equal to y1 to yn in Rn, x dot y, the standard inner product, is given by x1 y1 plus x2 y2 plus dot 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 xn yn. This is very similar to the standard dot product that you have studied in school. On Cn, there is a slight twist. The inner product is given not by the sum of the product of the corresponding coordinates, but you take a complex conjugation in the second variable. So this is complex conjugation. So recall that complex conjugation is just x plus iy bar is nothing but x minus iy. It will become very clear in a few slides why we are taking a complex conjugation when we are dealing with complex vector spaces, or more specifically when we are dealing with Cn. Now, modeled on the basic properties of the standard inner product, we define the general inner product on Rn. This general inner product is usually denoted an inner product. It's not the inner product. There are many on Rn and Cn. We denote it by these angular brackets, and these two dots are supposed to be the slots where you enter the vectors. Okay. An inner product is a map from Rn times Rn to R. It eats up a pair of vectors and spits out a scalar. It should satisfy the following conditions. When you take the inner product of V and W, it should be the same as the inner product of W and V. In other words, the inner product should be symmetric with respect to the two slots. The second property says when you take the inner product of u comma v plus v, you should get the inner product of uv plus the inner product of uw. The third property says that if you take the inner product of cv comma w, you should get c times inner product of v comma w. Okay, here c is a scalar coming from R. In addition, we will only consider inner products that are positive definite. That means the inner product of v dot v should always be greater than or equal to 0, and we must have equality if and only if v equal to 0. In other words, for any non-zero vector, the inner product v comma v should be greater than 0. Similarly, we have a complex inner product. It's a map from Cn cross Cn to C that satisfies the following properties. The inner product of v comma w should be equal to the inner product of w comma v conjugate. So let me just fix a minor error here. This is not Rn, this is just R. Sorry about that. So inner products take real values. Okay, that was a mistake. It's just from Rn cross Rn to R. So coming back to this complex inner product, and complex inner product is a map from Cn cross Cn to C that satisfies inner product of v comma w is equal to inner product of w comma v conjugate for all v comma w in Cn. So that is when you interchange the values in the slots, you get the same thing with a conjugate, however. And the second product just says that inner product of u comma v plus w is just inner product of u comma v plus u comma w. And the third property says inner product of CV comma W is just C times inner product of V comma W. This is for all C coming from the complex numbers. In addition, we will assume positive definiteness, that is that inner product of V comma V is greater than or equal to 0 with equality if and only V equal to 0. Here I must make a remark that V comma V is in general a complex number. So it doesn't make sense to say greater than or equal to 0 for a complex number. So what this condition V comma V greater than or equal to 0 essentially says is that it says that V comma V inner product should be real first of all. So that is sort of built in. When you write a complex number is greater than or equal to 0, you are actually asserting that that complex number is real also. So if you want to write this last condition more elaborately, what it is saying is inner product of V comma V is always real and greater than or equal to 0. Okay, so this is the general definition of an inner product. Let's see some first let me make some remarks, then we will see some examples. If you equip Rn with an inner product and you consider a vector V in Rn and fix that as the second slot, then you can see that this is a map. Now this is a map from Rn to R. That is, when you fix the second slot and you plug in things in the first slot, you get a map from Rn to R, and you can check from the properties of a real inner product that this map is going to be a linear transformation. So whenever you fix something in the second slot and treat the inner product as a function in the first slot, you get a linear transformation. Same thing applies when you fix the first slot with V and let the second slot vary. Okay, so this real inner product have the property that it is linear in both the slots. But there is a slight twist again for complex inner products, because we do not have symmetry, but rather we have conjugate symmetry. Inner product of V comma W is conjugate of inner product of W comma V. We get that the complex inner products are linear transformations only in the first slot. That means if you fix the second slot, you will get a linear transformation from Cn to C. However, if you fix the first slot, what happens is when you take V inner product CW, you get CW inner product V conjugate, which is actually equal to C conjugate inner product V comma W. Okay, check that what I have written is in fact a correct computation from the various properties of real and complex inner products. So there is this subtle difference between real inner products and complex inner products. Let's see some examples. You should check now that both the standard inner products on Rn as well as Cn are indeed inner products. Otherwise, this entire theory is sort of meaningless. We began with the dot product and said that inner products are extensions of the dot product. So please check that inner product, the standard inner products on Rn and Cn are both inner products. If you just take C, then the standard inner product is A comma B getting mapped to AB conjugate. Now this is important because when you take A dot A, the complex, in the complex case, you get mod A squared, which is a real number. Recall that we consider only inner products where inner product V comma V is always a real number and is greater than or equal to 0. If we had not put this conjugate, we will end up with a complex number in general. When you take a complex number A squared is usually also a complex number. So it is for this reason that we have imposed this additional requirement that when you have V comma W bar, when you take W comma V, it should be V comma W bar. The condition of there being a conjugate when you interchange the slots, and also in the standard inner product where we have put conjugates in the second place. So there is a reason for that, and this is that reason. Now for a more general example, consider A to be a real symmetric matrix, that is transpose of A is itself. then you can easily check that if you take two vectors v comma w in Rn and define v comma w inner product to be nothing but v a w transpose. Here I must remark that v comma w are treated as row vectors. They are treated as row vectors. Okay, so what I'm doing is I'm multiplying v with a and then I'm multiplying the product with w transpose. Check that this is actually going to satisfy all the conditions of the inner product except for positive definiteness. It will not in general be positive definite. We will see later that the above thing defines a positive definite inner product if and only if all the eigenvalues of A are positive. We will also see that for a real symmetric matrix, the eigenvalues are all real. Okay, we need all the eigenvalues to be positive for this to be an inner product. A concrete example of such an inner product is just take a diagonal matrix with positive entries. If you think about what this inner product will be when you take A to be a diagonal matrix with positive entries, it will be very similar to the usual inner product except some of the terms are scaled. That is, in other words, when you take x dot y, you may get lambda 1 x1 v y1 plus lambda 2 x2 v y2 plus dot 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 lambda n xn yn, where lambda 1 to lambda n are some positive real numbers. Now, the reason why such even a trivial generalization of the dot product is useful is, in general, when you're studying linear algebra, the various coordinates will not be of the same units. For instance, one of the coordinates could denote something in hours, the other coordinate could denote something in dollars, a third coordinate could denote something in some quantity of some raw ingredient. So the different axes could have different units. So maybe these lambda 1 to lambda n are some common factors that allow you to normalize. Maybe 1 hour of work is same as $20. So you can use these lambda 1 to lambda n to sort of normalize the various coordinates. So even this trivial dot product, where you have just taken the usual dot product and multiplied by various constants lambda 1 to lambda n, even that itself is useful in the real world. Okay, now we come to the geometry part. I had mentioned that inner product spaces allow you to study geometry on vector spaces. So we will consider an inner product on Rn or Cn, and using this inner product we are going to define the norm of a vector v in Rn or Cn. The norm is nothing but the length of that vector, and this is defined using this formula that norm v. The notation for norm is these two parallel vertical lines. So the absolute value is just two parallel lines. Here we have a pair of parallel lines. Okay, so this is just to denote that this is the norm. So norm of v is just square root of inner product v with v. Now note that inner product v with v is always positive by our positive definiteness condition. So this actually makes sense. You can actually take a square root. And you can also easily see that if you scale a vector, you know that the length should also scale appropriately, and that indeed happens with our definition, because inner product of CV comma CV would be just mod c squared inner product v comma v. The reason why I have put a mod c squared is I want to deal with both the Rn and Cn case simultaneously. In the Cn case, when you take c outside from the second slot, you will just get c conjugate. You won't always get c. So c times c conjugate will be mod c squared, and you will end up with mod c times norm v. So this is the definition of the length or norm of a vector. We can also define orthogonality. Orthogonality is just perpendicular. It is just a fancier term for the thing called perpendicular. We have studied very much in our school. Given an inner product on Rn or Cn, we say two vectors v comma w are orthogonal, and we will denote this by v perpendicular w, which is the usual notation, if the inner product of v and w is 0. Note that this is actually a symmetric condition. If v is perpendicular to w, if and only if w is perpendicular to v. You can check this quite easily. The idea of orthogonality comes from the fact that the standard dot product on R2 is given by xy cos theta, and the two vectors x and y will be perpendicular to each other only if cos theta is 0, in other words theta is pi by 2. So this is sort of an extension of the familiar geometry of the dot product in R2. Now the notion of length and orthogonality are exactly the standard ones when you consider the inner product. In particular, if you take a vector v equal to v1 to vn in Rn or Cn, you can check that the norm of this vector is nothing but under root mod v1 squared plus dot 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 mod vn squared, which is nothing but the length of the vector, as you can see by applying the Pythagorean theorem, the standard Pythagorean theorem for right triangles. Just do it for R2 to see that this is indeed the length of the vector v, or the distance of the vector tip of the vector v to the origin. Now, talking about the Pythagoras theorem, we also have a general Pythagoras theorem for an arbitrary inner product. So what you do is you equip v, which is Rn or Cn, with any inner product. It doesn't matter what it is. Suppose you take two vectors v and w that are orthogonal. That is, the inner product of v comma w is 0. Then observe that norm of v plus w is by definition that just under root v plus w inner product v plus w, and using the fact that this inner product is going to be linear, what I'm doing is I'm expanding out the whole thing term by term. So you will get v comma v, that's just this combined with this. Then you will get w comma w, that's just this combined with this. Then you get v comma w, that's just this combined with this. Then you will get w comma v, that's just this combined with this. I have just expanded out using the various properties of the inner product. I get this huge thing. But wait a second, this v comma v is just mod v squared, w comma w is just mod w squared, and these two are just 0 because v and w are orthogonal. So we immediately get that norm of v plus w is under root norm v squared plus norm w squared. Squaring, we get the classical Pythagoras theorem for inner product spaces also, that norm of v plus w the whole squared is norm v squared plus norm w squared. Now, just like using the dot product, we can define the notion of component of one vector on the other. We can do the same thing in an inner product space. So fix a vector v which is non-zero. Any vector w in v can be written as a sum of two vectors v1 and v2, where the first vector is along v. That means it's just some scalar multiple of v, where c comes from f. This f is either r or c depending on whether we are in a complex case or a real case. And the second vector v2 is perpendicular to v. So essentially what we are saying is, given any vector v that is non-zero, you can decompose any other vector w as a vector along v and as a vector perpendicular or orthogonal to v. Okay. To see why this is true, let's first try to find out a c, a scalar, such that w minus cv is in fact perpendicular to v, right? The idea behind that is we want to write w as just w minus cv plus cv for this scalar. Then we would be done. So solving, what we get is w minus cv comma v, which is just w inner product v minus c norm v squared. This should be 0. Right? Because we want w minus cv to be orthogonal to v. Immediately we get that c must be inner product wv by norm v squared. In other words, the component of w along v is nothing but cv, which is wv by norm v squared v. This is the component of w along v. And the component perpendicular to v is just w minus this. Okay. In particular, if you take norm v equal to 1, which is known as a unit vector, vectors for which norm v equal to 1 is called a unit vector, then the component of w along v is just the inner product of w comma v. This should ring bells, and you must recall similar stuff you have studied for the dot product in R2. Now we come to a very important inequality called the Cauchy-Schwarz inequality. The proof is slightly tricky. Let's run through the proof. what I will do is I will not even state the Cauchy-Schwarz inequality because it will not be clear how one arrives at such an inequality. What I'm going to do is I'll perform a computation that will sort of end with the Cauchy-Schwarz inequality. So what you do is you start with two unit vectors v and w, and let's do a computation. Let's try to find out what inner product of v minus w is. Certainly this quantity is going to be greater than or equal to 0 by positive definiteness, and expanding it out by using the various properties of the inner product, v and v will combine to get mod v squared, minus w and minus w will combine to get norm w squared. Then you will get a minus w inner product v and a v inner product minus w. Both of them will have negative signs. Okay. Now here observe that the conjugate of a real number is real. Conjugate of real number is real, obviously. And if you have a complex number z equal to x plus iy, then real part of z is nothing but z plus z conjugate by 2. This is something that you have learnt in your school when you studied complex numbers. Okay. Now, because the conjugate of a real number is itself, even in the real setting, I can write v dot w as w dot v, or sorry, I can just write this as vw. Again, I'm making a mistake. I can write this as wv conjugate, even if vw is a real number. If it's a real number, vw conjugate, wv conjugate is just wv, which is just same as vw when we are in the real setting. Okay. So why I want to do this is I want to combine these two. I want to combine these two terms and just write this as twice real part of v dot w. Twice real part v inner product w. Now this will be true irrespective of whether we are in the real setting or in the complex setting from the discussion that we just had. Okay. Now this real part of vw is certainly going to be less than modulus of vw. Correct? This is applicable both in the real setting as well as the complex setting. So net upshot is, because we considered unit vectors, both of these quantities, norm v squared and norm w squared, both of those will be 1. This will combine together to get twice real part of vw, which is less than or equal to absolute value of inner product v comma w. Okay. And the net upshot is 1 is equal to norm v times norm w is greater than or equal to modulus of inner product v comma w. So we have got this final inequality that absolute value of inner product v comma w is less than or equal to norm v norm w. This is true when v and w are in unit vectors, that is norm v equal to norm w equal to 1. Suppose one of these vectors were 0. If either v or w is 0, then observe that the right hand side will be immediately 0 because norm of a 0 vector is 0. Right? Therefore, this inequality will obviously be true if one of v or w is 0. The right hand side will be 0 obviously, and the left hand side will be, for obvious reasons, 0 as well, because you can pull out that scalar 0 outside and show that whenever you have a vector v and you take inner product with 0, you get 0. So this inequality will be true for obvious reasons when one of the vectors is 0. So assume now that neither of these vectors are 0, and we are going to try to show the same inequality. Okay. What you do is we reduce it to the case of unit vectors by considering inner product v by norm v comma w by norm v. Both of these will be unit vectors, simply because when you take v by norm v, inner product v by norm v, you will get 1 by norm v squared, inner product v dot v, which is just 1. Okay. So whenever you have inner two unit vectors, we have v by norm v comma w by norm w is less than or equal to 1 from what we have established. Now taking this 1 by norm v and 1 by norm w outside and taking it to the right hand side, we immediately get the inequality. Absolute value of inner product v comma w is less than or equal to norm v times norm w, and this inequality is true irrespective of whether v is a unit vector, w is a unit vector, v is 0, w is 0. This is always true. So this famous inequality is called the Cauchy-Schwarz inequality. In fact, this inequality is not obvious even when we had taken just the standard inner product on Rn or Cn. For instance, if you take v1 to vn, w1 to wn and Rn, the Cauchy-Schwarz inequality is saying that absolute value of v1 w1 plus dot 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 vn wn is less than or equal to v1 squared plus dot 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 vn squared multiplied by w1 squared plus dot 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 wn squared. This fact is not obvious. Just by looking at it, it's not clear that it's true. The Cauchy-Schwarz immediately gives us a triangle inequality. This triangle inequality is modeled on the geometric fact that the sum of two sides of a triangle exceeds the third side. So what it says is, given vectors v comma w in v, here v is Rn or Cn with some inner product, we have norm v plus w squared is nothing but inner product v plus w with itself, which will again give, by the same computations that we have done several times before, this will give mod v squared mod w squared twice real part of vw. Now what I do is this twice real part of vw, again what I do is I just equate it and say this term, I have skipped a step here, this is just less than or equal to norm v squared plus norm w squared plus twice modulus inner product vw. The real part is always less than the absolute value. Okay, now by the Cauchy-Schwarz inequality, we get the next step. This inner product v comma w absolute value is less than or equal to norm v norm w. And now we can just complete the square. You get norm v plus norm w the whole square. Taking square roots, we immediately get that norm of v plus w is less than or equal to norm v plus norm w, which is the triangle inequality. Now we come to the next interesting topic, which is called an orthogonal set of vectors. Let V be an inner product space, that is, it's either Rn or Cn equipped with some inner product, and let S subset of W be some set of vectors, none of which are 0. The 0 vector is not an element of this set S. We say that S is an orthogonal set if whenever you take two vectors V comma W from this set S and V is not equal to W, then V must be perpendicular to W. V must be orthogonal to W. That means any two distinct elements in this set S must be orthogonal, or any two elements are pairwise orthogonal coming from this set. Now one interesting remark about an orthogonal set of vectors is, if you take k orthogonal vectors, then they must be linearly independent. For instance, suppose c1 v1 plus dot 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 ck vk is 0, then what I do is I just take inner product of this. I just take inner product c1 v1 plus dot 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 ck vk with, let's say, v1. If I take inner product with v1, what I get is that I will get c1 inner product v1 v1 plus dot dot dot. I will not plus c2 inner product v1 v2 plus dot 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 ck inner product v1 vk v1. So this is actually, to be 100% correct, v2 v1. Okay, so the final term is inner product ck vk v1. But these are pairwise orthogonal. That means all these terms just vanish. And we are left with c1 inner product v1 v1, and since v1 is not 0, this is crucial, this is not 0. Okay, unless c1 is 0, right? And repeating this argument for each vi, we conclude that all the coefficients c1 to ck must be 0. So if you take k orthogonal vectors, pairwise orthogonal vectors, none of which are 0, they must be linearly independent. Now, if you take the standard inner product on Rn and consider the standard basis, a 30-second check will tell you that each of these standard unit vectors Ei is each one of these vectors is a unit vector, and furthermore Ei is orthogonal to Ej whenever I is not equal to j. Okay. Now equip Rn or Cn with some inner product. We say a basis V1 to Vn of V is an orthonormal basis if each Vi is a unit vector and Vi perpendicular to Vj whenever I is not equal to j. So we are mimicking the definition of an orthonormal basis on the nice properties that E1 to En have with respect to the standard inner product. There is a very big advantage we get by working with an orthonormal basis. Computations become extremely easy whenever you have an orthonormal basis for an inner product space V. For instance, if V1 to Vn is an orthonormal basis, then any vector V in V can be easily written down in terms of this basis. The coefficients, that is the coordinate vectors, are nothing but V inner product with Vn, V inner product with V2, V inner product with Vn. Okay, why is this true? Let's see a proof. Suppose V is A1 V1 plus An Vn. We know that V1 to Vn is a basis, therefore you can write any vector V like this. Then we pull the same trick we have done once before. We take inner product of V with V1. And expanding it out, we will get A1 inner product V1 V1 plus An inner product Vn V1. Because this is an orthonormal basis, Vi Vj are perpendicular whenever I is not equal to j. So all these other terms will just vanish. They will just vanish and we will be just left with A1 V1 inner product with itself. But V1 inner product with itself is just going to be 1 because V1 is a unit vector. This is an orthonormal basis. So we have already assumed that the orthonormal basis is something that each Vi should be a unit vector. Okay. So we get that A1 should be nothing, this V inner product with V1 is nothing but A1. The same argument will show that Ai must be V inner product with Vi. So we can write down the coordinate vectors whenever you have an orthonormal basis very easily. Another advantage of working with an orthonormal basis is even the inner product becomes really simple. If you have two vectors V and W whose coordinate vectors are A1 to An and B1 to Bn with respect to the orthonormal basis V1 to Vn, then doing the same condition inner product trick that we have pulled, when you do V comma W and expand everything out, it will be immediate to see that this is nothing but A1 B1 plus An Bn. So what this says is that whenever you are in an orthonormal basis, the inner product behaves very much like the standard inner product on Rn or Cn. So the existence of an orthonormal basis is really useful for computational purposes. So this concludes video 1. In video 2, I give a theorem, the famous Gram-Schmidt orthonormalization procedure, that allows you to construct an orthonormal basis for an inner product space. Thank you.